in our previous video, we have derived the potential due to point charge, potential due to dipole at any point at axial line, at equatorial line. Today we will derive the potential due to system of charges. Suppose this is any point is placed here where we have to find the potential and we are taking at V. Now, some charges are distributed like Q1, Q2, Q3 and so on Qn. And the distance from this point to this charge, that is R1, that is R2, that is R3, that is Rn. Now find out the potential, the net potential in this point. What we will do, we simply find the potential because of indivisible charges. Okay, because of this Q1, the potential is V1, we are marking it V1, and we have already derived in our previous video for potential due to point charge. Because of this charge, the potential will be 1 by 4 pi epsilon naught Q1 upon R1, V2 equal to 1 by 4 pi epsilon naught Q2 upon R2. In this point, because of this charge Q2, simply V3 because of Q3, that is 1 by 4 pi epsilon naught Q3 upon R3 up to Vn. So Vn will be 1 by 4 pi epsilon naught Qn upon Rn. Okay, previously we have already derived the electric field forces due to system of charges. What we have done there, we have simply applied the superposition theorem. Here we will apply the same theorem, superposition theorem. So net potential will be summation of all potential, that is V1 plus V2 plus V3 plus Vn up to Vn. Right, now simply we will put the values, equations, that is 1 by 4 pi epsilon naught Q1 upon R1 plus 1 by 4 pi epsilon naught Q2 upon R2 plus 1 by 4 pi epsilon naught Q3 upon R3 up to 1 by 4 pi epsilon naught Q1 upon Rn. Now simply this constant we will take outside the bracket. So V will be 1 by 4 pi epsilon naught, that is Q1 upon R1, Q2 upon R2, Q3 upon R3 up to Qn upon Rn. Right? So here we can write it in the form of summation, in the form of sum, that is 1 by 4 pi epsilon naught summation of I equal to 1 because it has started from 1 and goes up to n. So 1 to n, that is Qi upon Ri. This is the formula, basic expression for the potential due to system of charges where I will lie from 1 to n. Here we will simply put the 1. So it will become Q1 upon R1, then again we will put the 2 and then 3 and 4 up to m. It will goes up to m. So this is the basic potential due to system of charges. Okay, just note it down or take a screenshot. Now suppose charges are distributed uniformly like this. It will go like this. If charges are distributed uniformly, it will go like this and it will create this kind of surface, that is a spherical shell. It is creating a spherical shell. And suppose any charge Q is placed here and we have to find the potential in this point. We are marking P simply. and from this point to this Q charge has a radius r, and from this point to this the distance is small r we are taking. Now to find the potential outside the shell, this is the point which is placed outside the shell. To find the potential outside the shell, then we simply get the potential, that is 1 by 4 pi epsilon naught, and the charge will be q upon the distance. Now which distance we will take? Now we are talking about the potential outside the shell, so simply this small r will be get greater than capital R. Okay, so we will take this distance and we simply put here r. This is the potential outside the shell. Now suppose any point is placed inside the shell, and now in this point we have to find the potential. Again we are taking radius r, distance r. So then inside the shell the potential will be V equal to 1 by 4 pi epsilon naught, and Q will be remaining. Now in this case the capital R will be greater than small r. So here we will take distance capital R. Okay. When the charges are distributed uniformly, and to find out the any potential outside the shell, then we will consider this R will goes like this, and it will be greater than this R as compared to this. So we will take this R, and to find the potential inside the shell, then R will be smaller than capital R, and we will take capital R in the place of distance. Okay, is that clear? Take a screenshot. Now we will see the equipotential surface. We will see equipotential surface. Any charge q is placed here. Okay, and we have to find the potential in this point. We are marking P, and the distance between the points are R. So the potential will be simply by formula, that is Q by 4 pi epsilon naught R. Okay, now again we have to find the potential in this point, and the both points are again with same distance, that is R. So the potential will be Q by 4 pi epsilon naught R. The potential from both points are similar because the points are placed in same distance from this Q. Again any point with same distance, any point with same distance, and we have to find the potential, and these all points are placed in same distance from Q, that is R. So the potential will be similar for every point, and if we will join like this, we will get the shape of a sphere. We will get the shape of a sphere. So you can say the potential in every point is similar. So this surface is act as a equipotential surface. Again if we will go like this, if we will go like this, this is the equipotential surface, this is the equipotential surface, because from this point the distance in each and every point is similar. So this is the equipotential surface, this is the equipotential surface, this is also equipotential surface. It will form like this. So what we can write the definition of equipotential surface. Equipotential surface is the imaginary surface. Equipotential surface is the imaginary surface where at every point we will get same potential. In every point we will get same potential. Equipotential surface is the imaginary surface where at every point we will get same potential. Get it? Just take a screenshot. Okay, now these are the equipotential surfaces. It is appearing like this and charge Q is at center, is placed in a center. Now you can see here that every point having same potential, but if we will go far like this, these R lines are appearing parallel to each other, right? And if we will go far away, we will get the parallel lines. So equipotential surfaces are parallel to each other and they are appearing in the form of parallel lines. Here it is also making a parallel lines, but it is in the form of curve. That's why it is appearing in a very small amount. The parallel lines are appearing here, but it is in a very small amount. If we will go far from this point, we will see the parallel lines like this. The equipotential surfaces will appear parallelly to each other. Okay, this is clear. So just note down this point. Equipotential surfaces are appear in the form of parallel lines to each other. Now we will see the characteristic of this equipotential surfaces. Okay, this is equipotential surface and we know the electric field will appear like this. This is the electric field direction, outward radiated, and this is equipotential surface. Here you can see these two lines are perpendicular to each other, right? Which means it is making 90-degree angle. So you can write equipotential surfaces are perpendicular to electric field, or you can say electric field is perpendicular to equipotential surface. Both statements are right. Now suppose the potential in this point is V1, potential in this point is V2, potential in this point is V3, and potential in this point is V4. So which point has high potential? This point, which is very near to this Q, it has a high potential. So it will be always V1 greater than V2, greater than V3, greater than V4. You get it? The point which is very far from this Q, it has a smallest potential, which is very near to this, it has very high potential. Okay? And direction of electric field will be from higher potential to lower potential. Direction of electric field, it is always appear like this. So this is the direction. If suppose this is the direction of electric field, so it will always appear from high potential to low potential. So direction of electric field from high potential to low potential. Is that clear? This is the 2 points. First was the equipotential surfaces are perpendicular to electric field, or electric fields are perpendicular to equipotential surfaces. They will make a 90-degree angle to each other. Now second is direction of electric field from high potential to low potential will always appear from high potential to low potential. This is high potential, it has low potential, so it will always appear like this. Okay, now these 2 points are clear. Now it has a third point. Just take a screenshot or note it down. Suppose this is the equipotential surface. Any charge is placed here, that is Q. To bring this charge from this point to this point, we are taking this path, and other equipotential surfaces are distributed like this, right? And this is the direction of electric field, that is perpendicular to this surface, perpendicular to equipotential surface. Now you are seeing we are bringing this charge from this point to this point, and the both points are lying in the same equipotential surface. So how we will find the work done here? If we are bringing this charge from this point to this point, we have done some work done here. So we will definitely find it by work energy theorem, that says the work done will be equal to the difference of the energy. So here the energy is E1 and here the energy is E2. So for this, energy will be QV1 and here the energy will be QV2. And if it is equipotential surface, then V1 equal to V2. V1 will be equal to V2 and we are taking it V. So energy E1 is QV and energy E2 is QV. The both energy are similar, so the work done is difference between the energy, that is E2 minus E1, that is QV minus QV, that is 0. So the net work will be 0 to bring this charge from this point to this point in same equipotential surface. Okay, this is the third point, third characteristic. Now suppose these are the equipotential surfaces, right? Any charge is placed here and now we are taking this path and we are bringing the charge from this point to this point. So what will be the work done? It is work will be 0. Why? Because both points are in the same surface with same equipotential surface. So work will be 0. Okay. Now suppose these are the equipotential surfaces. Now we are just bringing any point charge Q from this point to this point. Now bringing from this point to this point, and then again we came in this point. So what will be the network? Network will be 0 because whatever path we are taking, we are coming from this point to this point, then our initial and final points are in the same equipotential surfaces. That means the network will become 0. Right? Is it clear? So this was the third point. Now just take a screenshot. Now we will see the relation between electric field and potential. We will see relation between electric field and potential. Find the relation between electric field and potential. The same diagram we will draw, which we have already drawn in previous, to finding the potential due to point charge. So where any plus q charge was placed in some point, and here we have taken a point P where we have to find the potential, and infinite there is a q naught, the test charge was placed, right? The distance between plus q charge and P is R. Now here, to finding the force, that was somehow difficult. So what we have done initially, we bring that q naught charge from infinite to some certain point, that is n, right? And the displacement we have taken, that is very small, that is dx, which has some direction, and it is in the form of this, and the direction will be in this direction. So from this q point to this, we have simply taken the distance x. Okay. So work done has been applied, which is very small. If electric field in this direction, why? Because this is positive q charge and it will be always outward radiated, right? And the force direction will be in the same direction, because this is positive q charge and q naught is also positive, we consider it. So this positive charge will repel this and the force direction will be in this direction, and electric field will be in the same direction, and the work done will be applied in the opposite to this force, that is dw, very small work done, right? Now dw is equal to a small work done x. We know force into displacement, we simply take force into, and displacement is very small, that is dx, and the angle between both is, this is the direction of field, force, and this is the direction of dw, or you can say the direction of x, displacement. So angle is 180 degree. So here we simply put, in the place of theta is 180, that will be f dx cos 180, and cos 180 is minus 1. We know the value, that is minus f dx. Now this f we will express in the form of electric field, and we know f equal to E into Q, electric field into Q. Simply here we will place it. So it will become EQ dx minus EQ dx, that is dw, right? Is that clear? We are just taking it equation 1. Now we know the potential, the formula for potential is work done because of, this is q naught, work done because of, to bring this q naught from one point to another point, that is work done upon per unit charge, that is w by q naught. Here we are taking a small work done, so we will take a small potential, so that will be dw into dv. Now we just multiply this q naught with dw, that is d, and so dw become dv q naught dv, and we are marking this equation number 2, and here dw value is q naught dv and dw is minus q minus e q naught dx. Now we will simply equate the both equation, so it will become q naught dv equal to minus e q naught dx. This q naught will be cancelled out. So what we will get in the form of E, that will be E equal to, this minus will come here, that will be minus dV upon, and this dx will divide with dV, that will be minus dV upon dx. This is the relation between electric field and potential. Simply what we have seen here, potential upon length, a small potential upon a small length. Now here we are talking about length, which means in the combined way we can say it potential gradient, because here we are seeing the length, so we can write it potential gradient. So sometime they ask in exam, find the relation between electric field and potential, or they will ask relation between electric field and potential gradient. So both are the same. Okay, and sometimes they just gave you the equation E equal to minus dV dx, and they will ask to prove this derivation, right? Now some characteristic for this potential gradient and electric field. Here first thing you are seeing that electric field and this potential gradient are in the form of minus, which means it is in the decreasing manner. So if we will see a equipotential surface, the V1 is, this is V2, this is V3. So it will be always in a decreasing manner. When we will go far from this point, the potential difference will be decreases. That is V1 less than V1 will be greater than V2, and V2 will be greater than V3. So it is in a decreasing manner. So this final sign is showing that it is going to in a decreasing manner, and this electric field will be always appear from higher potential to lower potential. The direction will be this electric field direction. This is the high potential, V1 is high potential and V3 is smallest potential. So it will be always appear from high to low potential. And the another point is here you can see E equal to minus dV by dx. So this dV by dx we can write, for dV we know the unit volt and dx meter. So for electric field we can write this unit volt per meter. This is also right. So these are the 3 points which is showing the characteristic between relation between electric field and potential, and it has some characteristic. First was it is in minus, this potential is minus, which is showing it is in a decreasing form, right? When the length will get increase, the potential will get decrease, and it will always appear from high potential to low potential. The electric field is always appear from high potential to low potential. In third point, we can also write the unit of electric field in the form of volt per meter because of this formula. Bye.